A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth. Comet, asteroid, or something else.
When NASA's instruments first captured the behavior of 3I/Atlas, scientists anticipated an ordinary data stream of a visiting interstellar comet drifting quietly through the solar system. Instead, they found themselves staring at something far stranger. The tail of the comet was not simply streaming outward as sunlight pushed dust and gas away from the nucleus. It appeared to be acting as if it were a propulsion system, creating thrust-like motions and altering the body's path in subtle but measurable ways. For a discipline that thrives on predictable mechanics, this was nothing short of stunning. A comet's tail is supposed to be reactive, not directive. To see it behaving as though it were driving the object forward challenged assumptions about how such bodies interact with stellar radiation and interstellar material. Before we start, smash the like and subscribe buttons for more updates. The discovery raised immediate questions about the physics governing cometary tails. Typically, tails form when solar energy heats the comet's icy surface, releasing gases and dust. Radiation pressure and the solar wind then push those particles outward, forming the classic glowing streaks visible to telescopes. The motion is passive, like smoke caught in a breeze. But in the case of 3I/Atlas, measurements suggested that its tail wasn't simply being blown back, it was aligning and adjusting in ways that seemed coordinated with its trajectory. This suggested a feedback loop between the ejection of material and the comet's motion, an effect much closer to controlled propulsion than random dispersion. To planetary scientists, the implication was unnerving. Celestial bodies are supposed to follow paths dictated by gravity and basic outgassing forces. If a comet's tail can act in a way that resembles thrust, then the boundary between passive natural object and active mechanism becomes blurry. NASA's admission that 3I/Atlas displayed such behavior added fuel to an already simmering debate sparked years earlier by the passage of 1Oumuamua, another interstellar visitor that had also shown non-gravitational acceleration. With Atlas, the evidence was harder to dismiss as observational error. The physics behind this phenomenon forced researchers to re-examine their models. Could the comet's composition contain materials that, when heated, expelled gases in highly collimated jets? If so, why would those jets act in such a persistent directional way instead of scattering randomly? One theory was that the comet's structure contained fissures that naturally funneled sublimated gases, effectively turning it into a self-stabilizing thruster. Another suggested that interaction with magnetic fields or charged particles might create asymmetrical forces on the tail. Yet neither explanation fully accounted for the repeated observations. Beyond the scientific puzzle, the cultural weight of NASA's admission was massive. People are accustomed to comets being passive wanderers. The sight of a glowing tail streaking across the night sky is supposed to evoke timeless wonder, not questions of propulsion. To suggest that such a tail could drive the comet through space stirred both fascination and unease. It opened discussions about how interstellar bodies might carry mechanisms unknown to us, whether natural or otherwise. Astronomers noted that interstellar comets, unlike those born in our solar system, may have formed in radically different environments. Their chemistry might include exotic compounds capable of reactions we do not expect. If 3I/Atlas originated in a dense star-forming region, it could have incorporated volatile ices that respond to heat or radiation in unusual ways. The tail, in that case, might be less a mystery and more a window into physics untested in laboratories on Earth. But the way the effect mirrored engineered propulsion remained an unsettling coincidence. NASA's cautious wording only deepened the intrigue. They refrained from speculation beyond acknowledging that the tail displayed propulsion-like characteristics. That careful phrasing indicated both scientific restraint and recognition of the extraordinary implications. For a government space agency that usually prefers conservative explanations, such an admission marked a rare moment of openness to the possibility that nature may be operating in ways far outside our current frameworks. The event also had profound implications for how humanity approaches interstellar visitors. If one comet can display tail-driven propulsion, then others may as well. This challenges existing strategies for predicting their paths. Small deviations from gravity-driven orbits amplified over long distances could change close approach forecasts in unpredictable ways. For planetary defense planners who must assess whether an object poses a threat to Earth, this represents a serious complication. A body that can subtly adjust its course through natural or quasi-natural propulsion introduces uncertainties into impact probability models. Another layer of the mystery involved the comet's interaction with sunlight. Normally, tails form two distinct components: a dust tail pushed by radiation pressure and an ion tail carried along magnetic field lines of the solar wind. In Atlas, the distinction seemed blurred. The tail appeared to act as a single coherent system, with streams moving not merely away from the sun, but in vectors that nudged the nucleus. That coherence suggested an internal order, as though the comet were aware of the forces acting on it. Though not conscious in any sense, the physical processes at play mimicked what engineers design into spacecraft to harness solar or plasma flows. The shock came not just from the observation itself, but from its confirmation. Multiple instruments across separate observatories recorded the same anomalous behavior. The redundancy eliminated the chance of error or misinterpretation. It was not a fluke of a single telescope or a software glitch. It was real, and it was happening in plain view of Earth's astronomers. For scientists, the puzzle became a test of humility. The cosmos repeatedly demonstrates phenomena that defy expectations, but there are few experiences more humbling than watching the sky and seeing a natural body perform in a way that resembles deliberate technology. Atlas forced experts to accept that the universe holds surprises even in domains thought to be well understood. Outgassing and cometary dynamics had been studied for centuries. Now, a single interstellar visitor had rewritten the assumptions. The philosophical implications could not be ignored. When nature and technology overlap in appearance, human imagination leaps toward the possibility of intent. If a tail acts like propulsion, people wonder whether it was designed to do so. NASA's admission stopped well short of endorsing such speculation, but it inevitably fueled public fascination. The notion that space might carry not only natural wanderers but also enigmas that resemble machines stirred discussions in both academic circles and popular culture. As the data poured in, researchers began to compare Atlas to historical records of comets observed centuries ago. Had similar anomalies been missed because of less precise instruments? If tails had ever acted this way before, ancient skywatchers would not have had the tools to notice. The thought that comets may have been quietly performing such feats for millennia was unsettling, as though humanity had lived alongside a cosmic mystery without realizing it. Some proposed that the propulsion-like effect might actually be a natural strategy for stability. In the vast emptiness of interstellar space, a comet could benefit from mechanisms that adjust its path, ensuring it avoids destructive collisions or maintains exposure to optimal radiation for sublimation. Such ideas seem speculative but open new avenues for thinking about how bodies adapt, even passively, to their environments over astronomical timescales. Meanwhile, NASA's willingness to label the phenomenon as propulsion-like carried scientific weight. Words matter in research. By choosing language that acknowledged the similarity to engineered systems, the agency signaled that the anomaly could not be brushed aside as a minor curiosity. It was significant enough to merit attention, funding, and further investigation. The act of formal recognition elevated the observation into a milestone event. The question then became what this meant for humanity's future in exploring interstellar objects. Missions to visit such bodies, once viewed as exotic luxuries, began to seem essential. If the solar system occasionally receives visitors carrying unexpected physics, then sending probes to examine them up close could yield discoveries impossible to replicate on Earth. Atlas reinforced the urgency of developing rapid response missions capable of intercepting these wanderers before they vanish back into the void. The behavior also touched on broader themes of propulsion itself. For decades, engineers have pursued solar sails, plasma drives, and exotic concepts that use radiation or particle flows for thrust. To see a natural object seemingly accomplish something similar suggested that nature may have already perfected techniques humans struggle to master. Observing and understanding those processes could inform future spacecraft design, turning cosmic anomalies into templates for innovation. In classrooms and lecture halls, Atlas became an immediate case study. Professors highlighted the event as an example of the scientific method confronting the unexpected. Data does not always conform to theory, and when it doesn't, the theories must evolve. Students were challenged to think beyond the textbook, to imagine explanations that combine physics, chemistry, and celestial dynamics in novel ways. In this sense, the comet served as a catalyst for intellectual growth. What made the event so compelling was not only the science, but also the imagery. Telescopes captured the shimmering plume stretching across the blackness, bending and twisting in ways that defied expectation. To the naked eye, it looked no different from any other comet, yet beneath that familiar glow lay forces no one could easily explain. The juxtaposition of normalcy and anomaly created an almost poetic tension, reminding humanity that mysteries can hide in plain sight. The comet's journey through the solar system was brief in cosmic terms, but its impact on human thought was immense. Each observation added new layers to the puzzle, drawing in not only astronomers, but also physicists, engineers, and philosophers. Everyone sought to grasp the meaning of a tale that acted like propulsion. Was it a rare quirk, or a glimpse into a pattern that would become familiar as more interstellar objects arrived? The more scientists studied Atlas, the more they realized that this single event could reshape entire fields. Models of cometary dynamics needed revision. Interstellar chemistry had to account for new behaviors. Planetary defense required updated strategies. Even the philosophy of science itself gained a new reminder of humility before the unknown. NASA's admission did not end the mystery, it amplified it. By openly stating what the data revealed, the agency ensured that the world's scientific community could no longer dismiss the anomaly as fringe speculation. Instead, it became a legitimate subject of inquiry, demanding rigorous exploration. Atlas's tail was no longer just a streak of gas and dust. It had become a symbol of the cosmos's capacity to surprise, to defy, and to inspire. As the comet receded into the distance, leaving behind its trail of questions, humanity was left with a deeper awareness of its place in the universe. The skies, once thought predictable in their patterns, had revealed a hidden complexity. A comet should not do this, and yet it did. That contradiction, hovering in the space between what is known and what is possible, marked one of the most fascinating astronomical revelations of recent times. When astronomers train their instruments on the vast black canvas of space, they expect to see behavior that falls neatly into the categories established by centuries of observation. Comets, asteroids, and interstellar objects each have their own expected dynamics. That expectation was shattered when 3I/Atlas revealed a tale that did not simply drift with the solar wind, but appeared to influence its own movement. Once the initial shock wore off, the deeper implications began to unfold. This was not a mere curiosity. It was a challenge to the very framework of how celestial motion is understood. The possibility that comets might act as natural thrusters introduces a new category of celestial dynamics. Instead of thinking of them as passive chunks of ice and dust, we must now entertain the idea that they are active participants in their journeys, adjusting course through mechanisms that, while natural, function like guidance systems. This blurs the boundary between organic and mechanical, suggesting that the line humanity draws between what is engineered and what emerges spontaneously from natural laws is thinner than once believed. The next layer of inquiry dealt with composition. A comet's tail is the visible evidence of its chemical makeup. If 3I/Atlas's tail behaves in a directed way, then its ices and volatiles must possess properties not typically seen in solar system comets. Imagine an exotic form of ice that sublimates in bursts instead of diffuse clouds. If the sublimation is directional, emerging through narrow channels, it could mimic the operation of a nozzle. Multiply this effect across a rotating body, and one could imagine a comet that maintains a consistent thrust vector, even as it spins. Such chemistry may be rare in the solar system, but common in other stellar nurseries. The comet thus becomes not only a traveler from another system, but a messenger carrying the physical fingerprints of alien environments. The implications for planetary science are profound. For decades, researchers have modeled planetary formation under the assumption that interstellar materials broadly resemble our own. If Atlas demonstrates otherwise, then every model must be updated to account for radically different volatile inventories. Planets forming in such systems might possess atmospheres, oceans, and climates unlike anything imagined in Earth-based models. The diversity of habitable conditions in the galaxy could be far greater than previously thought, and comets like Atlas provide the evidence. Engineers studying propulsion systems also found themselves drawn to the case. Humanity has long dreamed of interstellar travel, but one of the greatest barriers is fuel. Carrying enough propellant to cross the void is impractical. Instead, scientists have proposed using solar sails, ion drives, or harnessing interstellar resources. If Atlas's tail naturally produces propulsion, then it suggests a template for spacecraft design: vehicles that use controlled sublimation of exotic materials to generate thrust. The fact that nature may already be demonstrating this technique validates years of theoretical exploration. It also raises the possibility that humanity could one day harvest materials from such objects to power long-duration missions. Another striking implication is the challenge it poses to orbital predictions. In celestial mechanics, accuracy depends on assuming forces are consistent and predictable. If a comet generates thrust-like effects, then its future path is no longer dictated solely by gravity. Even small accelerations applied consistently over time can lead to dramatic deviations from expected orbits. This means that predicting the trajectory of interstellar comets will always carry uncertainty unless their propulsion-like mechanisms are fully understood. For planetary defense strategists, this creates an added layer of risk. An interstellar object with even a slight ability to alter its own path could turn a harmless flyby into a closer encounter, or vice versa, in ways that models cannot anticipate. Beyond science and engineering, the psychological impact cannot be ignored. Human beings are accustomed to thinking of celestial bodies as passive, unchanging actors in the cosmic theater. Stars burn, planets orbit, comets trail their luminous veils, and everything follows the silent rules of physics. But Atlas disrupted that picture. Suddenly, one of those seemingly passive wanderers was acting in ways eerily reminiscent of machines built by human hands. The sense of otherness was palpable, and it stirred a deep unease. It was no longer sufficient to assume that the heavens could be neatly categorized. Instead, the universe revealed itself to be capable of imitating intention, even in the absence of life or design. The philosophical ripples extended outward. Scholars in fields as diverse as theology, metaphysics, and anthropology began to weigh in. If natural bodies can exhibit behavior that looks purposeful, then how do we distinguish between what is designed and what is emergent? The question touches on the core of human perception. We look for patterns, infer purpose, and often equate control with intelligence. Atlas's tail reminded us that the universe can produce purpose-like outcomes without intent. It is a humbling reminder that what appears engineered might simply be another expression of natural law, one we have yet to fully grasp. Astronomers also consider the possibility that the phenomenon might be linked to the comet's origin environment. Imagine a system near a supernova remnant, where heavy elements and charged particles interact with frozen volatiles in unique ways. A comet born in such a crucible could inherit properties impossible to replicate in our solar system. If Atlas carries that legacy, then studying it is like holding a relic of a distant alien history. Every particle in its tail might contain clues about environments we will never visit. The propulsion-like behavior could therefore be an accidental byproduct of its birthplace rather than a feature of all interstellar comets. In practical terms, NASA's candid acknowledgement of the anomaly was groundbreaking. Space agencies often tread cautiously when presenting unexpected findings, preferring to cloak them in technical language until further data is gathered. By directly stating that the tail of Atlas behaved like propulsion, NASA demonstrated a rare willingness to call the phenomenon what it appeared to be. That choice of words carried enormous weight, signaling to the scientific community that this was not to be brushed aside as a minor curiosity. It demanded attention, funding, and rigorous investigation. The attention also shifted to the technology of observation. Detecting the subtle accelerations caused by a propulsion-like tail requires instruments of extraordinary precision. The fact that astronomers were able to measure these changes at all is a testament to the sophistication of modern telescopes and tracking systems. This success raises the bar for future missions. If interstellar objects can surprise us with such behavior, then humanity must be prepared to capture data quickly and comprehensively before they disappear back into the abyss. That means more automated sky surveys, faster data processing, and potentially space-based observatories dedicated solely to monitoring interstellar visitors. Cultural reactions reflected the blend of awe and unease. Media outlets seized on the story, framing it as evidence of cosmic mysteries that defy explanation. For the public, the idea of a comet acting like a spacecraft fed into long-standing fascinations with extraterrestrial technology. Though scientists did not claim any artificial origin, the resemblance was enough to ignite imaginations. Stories, discussions, and speculations flourished, demonstrating how deeply such anomalies resonate with human curiosity. The skies are not only scientific domains, they are also canvases for myth, story, and meaning. Atlas joined that lineage as a modern enigma. The mystery also emphasized the importance of humility in science. Humanity often assumes that the universe has revealed its major secrets and that only refinements remain. Atlas shattered that assumption by showing that even the most familiar objects, comets, can still surprise us with wholly unanticipated behavior. It was a reminder that exploration is not about confirming what we already believe, but about being open to whatever reality presents, no matter how strange. This event may also reshape priorities in space exploration. Interstellar objects had once been considered rare novelties, unlikely to influence broader strategies. But after the back-to-back appearances of Oumuamua and Atlas, followed by NASA's startling admission, it became clear that these visitors are both more common and more scientifically valuable than previously imagined. Future exploration missions may focus on developing rapid-response spacecraft capable of intercepting such bodies on short notice. If comets can carry propulsion-like phenomena, then understanding them becomes a frontier of space science with direct implications for physics, engineering, and perhaps even our concept of life in the universe. Another layer of intrigue comes from the fact that Atlas is only the third confirmed interstellar object observed passing through our solar system. With such a small sample size, each one becomes immensely important. If two of the three have already demonstrated anomalous accelerations, it suggests that what seems extraordinary may actually be typical. That possibility could rewrite our expectations about the dynamics of interstellar travel. Instead of imagining inert bodies drifting endlessly, we may need to view them as active participants in their journeys, subtly adjusting as they move through space. The potential connections to habitability and the origins of life are also worth considering. Comets are often theorized to play a role in delivering water and organic molecules to young planets. If interstellar comets can generate propulsion-like effects, then they may be more efficient carriers of such materials than previously thought. They could maneuver into systems in ways that maximize the likelihood of interacting with planets, seeding worlds with the ingredients of life. In this sense, Atlas's strange behavior may not only be a scientific curiosity, but also a clue about how life spreads across the galaxy. For the scientific community, the challenge now is to devise experiments and simulations that can replicate what was seen. Laboratory tests with exotic ices, vacuum chambers, and directed energy may reveal whether sublimation alone can account for the effect. Computer models may uncover whether asymmetrical outgassing could sustain a propulsion-like vector over time. The key is to distinguish between the merely unusual and the fundamentally new. If the effect can be explained by physics we already know, then Atlas simply expands the range of natural phenomena. If it cannot, then it points toward new laws waiting to be discovered. When the realization spread that 3I/Atlas's tail was not behaving like the classic diffuse stream of dust and plasma, it pushed entire research communities into uncharted territory. Each new dataset suggested that this was not an isolated fluke of observation or an instrument error, but a genuine feature of the object. To grapple with it, scientists began looking far beyond the conventional cometary model, reaching into disciplines not normally brought together. Fields as disparate as plasma physics, materials science, atmospheric chemistry, and even systems engineering. The phenomenon seemed to sit at the crossroads of multiple domains, forcing an interdisciplinary reckoning. One angle of inquiry that quickly gained attention was the role of plasma dynamics. In the solar system, ion tails are shaped by the solar wind, the charged stream flowing out from the sun at hundreds of kilometers per second. Normally, this creates a predictable pattern. Ions glow as they are swept into straight bluish tails aligned with the magnetic field lines of the wind. Atlas, however, appeared to show asymmetry, as though the ions were not simply being dragged, but instead forming coherent flows that imparted force on the nucleus. Plasma instabilities, such as reconnection events or self-organizing currents, might provide a natural explanation. If the comet's plasma environment was unusually active, perhaps because of unique chemical reactions, then its tail could act more like a magnetohydrodynamic engine than a passive plume. Geophysicists also weighed in, comparing the situation to jets of volcanic gas on Earth or geysers on icy moons like Enceladus. On those worlds, confined conduits channel pressurized material into directional plumes. Atlas could contain fractures or cavities acting as natural nozzles, focusing escaping gases in narrow streams that align with its rotation in ways that stabilize thrust. If this model proves correct, it would suggest that certain bodies, by sheer structural happenstance, evolve into natural propulsion systems. Such objects would not just wander aimlessly, but could, in a limited sense, steer themselves across interstellar distances. The idea of comets as semi-self-guided wanderers opens a fresh discussion about cosmic navigation. In interstellar space, survival is not trivial. Collisions, radiation, and gravitational perturbations threaten the integrity of small icy bodies. An object that can adjust its course even subtly might be more likely to persist long enough to reach other systems. In this light, Atlas's propulsion-like tail could be interpreted as a survival mechanism built into its structure by natural selection at a planetary scale. The cosmos, over billions of years, may favor bodies capable of persistence through adaptive physics, even without life or biology. Another dimension worth examining is the thermodynamics of unusual volatiles. Laboratory simulations have shown that certain exotic ices, such as frozen nitrogen, carbon monoxide, or even more complex hydrocarbons, sublimate at temperatures far lower than water ice. If Atlas contains abundant amounts of these compounds, then its tail might behave far differently from typical comets. For instance, jets of nitrogen gas, when funneled through narrow fractures, can generate thrust more efficiently than water vapor because of lower molecular weight and higher velocity outflow. The composition of Atlas could therefore be a key driver of the anomaly. Spectroscopic analysis hinted at unusual emissions, though much work remains to confirm the exact mix of volatiles. Astrobiology also finds a foothold in this puzzle. Comets have long been considered potential carriers of organic molecules, and interstellar comets are even more tantalizing because they bring chemistry from distant stellar neighborhoods. If Atlas's tail behavior arises from volatile compounds not commonly found in our system, then it may represent reservoirs of chemistry otherwise inaccessible to Earth-based laboratories. These compounds, interacting under unique energy conditions, could generate not only propulsion-like effects, but also prebiotic reactions that matter for the origins of life. A comet acting like a thruster may inadvertently be a vehicle for transporting the seeds of biology across interstellar space. The observational strategies employed also highlight the fragility of our understanding. Atlas was visible only for a short window, and much of what was learned came from hurried campaigns organized across observatories worldwide. That urgency underscored the need for coordinated networks that can mobilize instantly when interstellar visitors appear. The data collection must span wavelengths, from radio to infrared to ultraviolet, to capture the full spectrum of processes. If Atlas had been caught too late, the opportunity to witness its tail's strange, propulsion-like character might have slipped away entirely. This realization is motivating new global initiatives to prepare for the next interstellar object. In addition to scientific implications, Atlas inspired deep cultural reflection. Humanity has always interpreted the sky as both a map and a mirror, projecting hopes and fears onto celestial wanderers. Comets were once omens, symbols of change or upheaval. With Atlas, the tradition continues, though in a new guise. The fact that its tail mimicked propulsion led many to see it as a signpost of humanity's future in space, a reminder that even nature itself experiments with movement through the void. In literature, philosophy, and art, the image of a comet as a self-propelled traveler has already begun to take root, influencing how societies think about exploration and survival beyond Earth. A further intriguing aspect is the scale of the forces involved. The accelerations measured in Atlas were tiny, imperceptible to the naked eye. Yet across astronomical distances, such small nudges add up to massive deviations. This principle echoes what engineers call low-thrust propulsion, where spacecraft are gradually accelerated by ion engines or solar sails. The parallel is uncanny. Humanity designs machines to push gently over time, and now it finds that the cosmos produces natural bodies performing the same feat. The similarity suggests that universal physical principles govern efficiency, whether in human inventions or natural processes. The anomaly also highlights the importance of comparative study. With only 3 known interstellar objects, Oumuamua, Borisov, and Atlas, each one becomes a benchmark. Oumuamua displayed unexplained acceleration, though without a visible tail. Borisov resembled a more typical comet but still carried hints of unusual chemistry. Atlas combined visible outgassing with propulsion-like behavior, merging features of both. Together, they paint a picture of interstellar objects as a spectrum of phenomena rather than isolated oddities. If even this small sample has produced such variety, then the galaxy must teem with an astonishing diversity of wandering bodies, each with its own story written in ice and dust. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA's shocking admission about 3I/Atlas? We want to hear from you. Thank you for watching, and see you next time.